what the guys told me in 2003, I said, well, what can we do now? And they said, well, you're going to have to wait, if you can believe this, 3 to 5 years for this new technology to come on board, that instead of primers, it's going to do it base pair by base pair by base pair. And that's what you need, because if your thing has never been seen before, the base pairs are how it has to come out. You have to be able to pull it out base pair by base pair. Sure enough, almost three years to the month. That was July 2003. This is July 2006. A company called 454 Life Science announces that they have a technique for doing it. I'm not going to go into it. It doesn't matter. It's impossible. It's incredible. It's unbelievable how they do it. But they do it. They can pull it out. They can disassemble DNA base pair by base pair. It's just simply astounding. And then tell you what you have. Next slide. So, in early 2010, a new geneticist contacted me and offered to help using that new kind of equipment. From 2006, the first few of these things that were done, the first few genomes that were recovered were like $10, $15 million each. The price just was plummeting that whole time. So now it's down to maybe, to do ancient DNA, it's just a couple million. Now, a lot of people say, well, wait a minute, why does it cost so much to do the Starchild DNA when I read on the internet that I could, you can have your DNA done for $5,000, $10,000. Well, that's true. You can have your DNA, your genome sequence for about 10 grand right now using this equipment. Because it's fresh DNA. You saw the rubber band pile. All these things do is they unbuckle the rubber bands and just string them out and measure them. Fresh DNA, easy to do. Now, imagine when you're dead for a long time. Imagine that wad of rubber bands put through a wood chipper, and now all the little pieces. And that's what you've got to put together to make the genome of something that's been dead for a long time. And that's our problem. To do that, you have to do it again and again and again and again, 50 to 100 times. Run it through the machines 50 to 100 times so that you fill in every gap and you string the rubber bands back together. Basically, yeah. So that's why it costs so much. Next slide. Anyway, when he did, after a few weeks, he recovered and sequenced dozens of fragments of the nuclear DNA. That's all he got the first time. Dozens of fragments, but they were long, but they all came out of the junk. But they were in the hundreds. And so what he did was, when he got those dozens, he sent them all to what's called the NIH database. Next slide. The NIH is the National Institutes of Health in Maryland. And what they have is, in America, they put out the money to most labs to do DNA work. So that if you want to do some kind of work, they will give you the grant money to do it. And in doing so, you owe them the results. And they take the results and they put them in the database. So by 2010, when we were doing this, middle 2010, the database was very, very full of literally billions of coherent base pair strings to compare to. All of the human, all the chimp, all the gorilla, and parts of hundreds of other animals. So it had a very, very good spread, down to bacteria and yeast and molds and things like that. Everything anybody did, it went into that database and it was there. So if you had unusual DNA, that's what you did. You sent it there to see if it matched up with anything. Next slide. So what the Starchild did was, some of it did come back in strings that matched up in the human genome. Some of it did. This is one of 265 base pairs. Okay, and it says very clearly that 265 base pairs is found exactly matched in Homo sapiens chromosome 1 genomic contig here. They know where it is, right? But half of the things he sent in, next slide, half of them came back. This is a 342 base pair. No significant similarity found. Not on Earth. So he contacted me and he says, boy, you really got something here. He says, we can have a few of these maybe, but not half of them. He says, you've got something here. Let's go to work on it. And I told him, we don't have a pot to piss in. I'm sorry. But we can't get the kind of money you need. And he says, let me think about it. And that's when that plan of keeping the little pieces came up. To do it, to do it more seriously. So he began to do, he did another one. Next slide. Oh, excuse me, this is the next test he did. He was so excited, he did this test, and this is really cool, I think. Spectrophotometer illustrates light wave absorbance in pure DNA. This is how it looks, human DNA, this curve right here. This is how no DNA looks, and this is how protein contamination looks. And they all know how this goes. And so he just wanted to see how it would look. Next slide. And what you see is the human looks very much like it's supposed to look, but the Starchild looks like kind of a drunk snake, doesn't it? Just, what is it? It's not really no DNA, it's not protein contamination, it's not human, what is it? And this too, he said, this tells you, this is very unusual what you have here. I don't know what it is, but this is not normal. Very cool. Next slide. So, now let's go back and get back on track because we're going to start talking about mitochondrial DNA now. All right? So you've got to get back where we were. Remember, 3 billion base pairs in the nuclear DNA and 16,569 base pairs in the mitochondria. But that's where 95% of it works. That's where you don't get much change over time. And only females pass it on, etc. Next slide. So he recovered, in one of his next attempts, he recovered 4 fragments, 4, from mitochondrial DNA. 4. And the problem is, if it comes in junk, you can't figure anything out. You can't compare. You can't do anything. You've got to get it from the working parts to be able to compare it head up to what the human parts do. So, mitochondrial DNA is circular in design, and it is, and maintains astonishing efficiency, only about 5% is junk, which is more like 3%, that does nothing critically important to its functioning. 15 primary genes are very well understood. This is one of the best understood parts of your body. Each one of those, the RNAs, the NDAs, all that's very well understood. They encode for RNA. Mitochondrial DNA is extremely highly conserved. It undergoes so little change over time, those changes are used as the biological clock. You've heard about mitochondrial Eve. They take human females and they clock back their mitochondrial DNA, and the oldest DNA is found in black Africans of South Africa, just where Sitchin said the Anunnaki said they created us. That's where you find them genetically. And they're about 200,000 years old. That clock takes us back about 200,000 years to those black African women. Us, sitting here, 60, 70, 80, differences. Those have 120. The oldest of us have 120. We'll get to that. Next slide. All right. Human haplogroups. They're like 30, now you can sometimes get 33, 37, 38. People argue about the haplogroups, but these are the haplogroups right here. HPTA. Remember the haplogroup A for the human, haplogroup C for the Starchild, 2 basic ones, and we don't even know that that's their haplogroups, and these are the rest of the haplogroups. And here you see the human mitochondrial DNA from the Cambridge reference sequence. To get like the standard baseline, they picked one person and they did their mitochondrial DNA, and that became the baseline against which everything else was measured. Cambridge reference sequence, it was done at Cambridge. And then you have the Neanderthal mitochondrial DNA, and you have 2 of Denisova, the Denisova bone and the Denisova motor. Well, what is Denisova? Next slide. Surprise! Denisovans are a new addition to the early Homo prehuman family tree. If you haven't heard about them, they just got this finger bone and the tooth out of a cave, and they thought it was with Neanderthals, and they thought it was Neanderthal, but they measured its mitochondrial DNA, and its mitochondrial DNA was so different that they knew it had to be, even though they only had a little piece of finger bone and a tooth, it had to be another species. Just because mitochondrial DNA is so well conserved and everything fits within such a tight window of each species that if you're outside that window, you're something else. This is very significant. So Denisovans were discovered in 2010. They seem to have been contemporaries of Neanderthals. Their DNA exists up to the 5% level in modern Micronesians, Fijians, New Guineans, and Australian Aborigines, and new groups being discovered. This is very exciting in the world of anthropology. Next slide. And biology and genetics. Now, base pair nucleotides, get with this. 1,255 of 16,000. Let's say we had all 16,000 stretched out here one by one. We're going to take out this narrow slice from 1,255 to 1350. These 95 contain no variations in any haplogroup. They're clean. There are no changes. When we talk about highly conserved, that's what we mean. No changes over time in none of them. Very highly conserved across all 33 haplogroups, the one Neanderthal and the two Denisovans. Next slide. Now we're going to take another stretch. Oh, I want to show you what variation looks like. Variation in the human mitochondrial DNA. These lines come up, the computers do this automatically, but you see where everything else has a T, there's a C right here in this haplogroup. That's a variation. That is a variation. Keep that in mind. You can have them. You do have them. And over the whole course of the 16,000, humans have 120. Like that. Next slide. Okay, this is the other way they can be. They can be a change or they can be a missing. If there's a missing nucleotide, the computer automatically puts something in to show there's something different here. So you can either have a complete change or you can have just a missing spot. Up or down. You can see up or down. Up, down. Next slide. The computers know. Now here we have a different stretch. We have from 1426, well, from 1262 to 1426. This is, instead of 95 like the other one, this is 164 base pairs long. Now in this one we find that each of the Denisovans have one difference. You see it right there? The Neanderthal has one right here. That's C right there. And the human has one right here. That's C right here. Each of them have one. This is a very highly conserved area, but there is one change for everybody. Now we're going to see the Starchild's exact same segment right here. Next slide. 17 changes. 17 differences. You with me? Now right here, folks, this is a home run. Just right here. To show that it's not human, it's not Neanderthal, it's not Denisovan, it is something else. And Vivi came up with this great analogy that I'm going to use and going to share with you. It's as if the human, the Denisovans, and the Neanderthals, or at least in the States, this is how I know it. Let's say humans have an area code on their phone in Louisiana. Neanderthals have an area code in Tennessee. Denisovans have an area code in Pennsylvania. The Starchild's area code is on the moon! On the moon! It's that far away. You with me? It's that big a difference. Now we're going to see it in more detail, but this just shows you right here. It's very, very dramatic. Next slide.